Welcome back. This is our last section of notes on sound. First, we're going to investigate beats. These are something that are used for tuning instruments. Now, for beats, we want to think about what your ear is going to hear when beats are occurring. And in order to do that, I want you to review superposition. So our ear automatically adds the amplitudes of two waves together, so that sum of the amplitudes is what's called superposition. Now, if we have two waves and there happens to be a difference in their frequencies, your ear is going to hear a pulsing vibration in loudness. And we're going to do an activity in class where you'll actually hear what that pulsing sound is like. So you'll experience that firsthand. But for now, write down your definition for beat frequency. It is the difference in the frequencies of the two waves. And then our formula looks like this. Remember, delta means change, and we're simply going to subtract the two frequencies that are given. And notice I put absolute value signs here because when we hear beats, you will be unable to tell which frequency is larger and which one is smaller. You'll only know that there's a difference. So whenever we find the beat frequency, we're going to do the absolute value of the difference in those two frequencies. And you should still get units of hertz. Now I put an example problem in for you. It should be pretty simple to solve. We've got a 442 hertz tuning fork and a 444 hertz tuning fork. They are struck at the same time and you're asked to find the beat frequency. So take a moment and see what you get. Hopefully you got an answer of 2 hertz. This means on that pulsing sound, you would hear 2 pulses every second. Next, we're going to look at the speed of sound in air. At 0 degrees Celsius, sound travels at approximately 331.5 meters per second. You should remember from chemistry that as the temperature of something increases, those molecules can vibrate faster. So the same is going to be true for our sound waves. For each degree of temperature change, the sound will travel at a difference of 0.6 meters per second. So to come up with how to solve this, I have an example problem for you. We're looking for the speed of sound at 20 degrees Celsius. So first, we would want to see how much that's going to change our speed. So we multiply 20 degrees times our conversion factor of 0.6 meters per second for each degree, and that lets us know that our speed of sound is going to change by 12. To get the total speed, we're simply going to add that to our original value at 0 degrees. So we take our 331.5 and add 12 to it. So pause the video and add that together and come back and see if you get the right answer. You should have gotten 343.5 meters per second. Now I'm putting a star around this example problem and I highlighted for you. This is the value you're going to use for the speed of sound problems unless another temperature is indicated. And that's because 20 degrees is the accepted value for room temperature. So unless you're told otherwise, this will be the number that you want to plug in for how fast sound can travel. So we can summarize this overall. You would start with your 331.5 meters per second, and then you want to add our conversion factor of 0.6 times whatever temperature you're given. And we can use the speed of sound for distance over time problems or frequency times wavelength problems. Next, we're going to look at the Doppler effect. So I'll give you a moment to write down that definition. You can pause the video if you need to. So the Doppler effect is looking at the change in frequency produced by the relative motion of a source and an observer. So I don't know if you've ever been on the side of a road and a car goes whizzing by you really fast. You kind of hear the sound, so that pitch will change slightly. And that's what we're going to look at with the Doppler effect. So imagine that you've got some source right here and it emits a sound. Well, if it's not moving, those sound waves are going to travel out in all directions, and they can be represented by these concentric circles. So I gave you some variables over here to the side, and we're going to refer back to those, and you'll need to draw another picture in that blank section of your notes underneath this one. When we look at our wavelength, that's going to be the distance between any two of the circles. So I can label my wavelength in any direction. So it's the distance between any of these circles. Those are the crests. Now, once the thing that's making a sound starts moving, those sound waves are going to squish together and run into each other on one side as it moves toward an observer, and they'll spread out as it moves away from an observer. In your notes on the next page, it's going to ask you to identify the wavelength and the frequency when something is moving toward an observer or away from an observer. So remember that the distance between any two of our circles, which are the crest, is going to be the wavelength. So you should see that the wavelength is getting smaller over here because those circles are more squished together. And then on the other side, as you move away from an observer, the wavelength is getting bigger because those circles are spreading out away from each other. And now let's fill in the blanks for the next section. So as we look at a source moving toward an observer, that's when the wavelength is decreasing because the circles get squished together. And remember, wavelength and frequency are opposites to each other. So if the wavelength is smaller, that means the frequency is bigger. And also recall that frequency and pitch are the same thing. So if we have a larger frequency, that's going to result in a higher pitch. You do have a formula for figuring out what frequency is heard by the observer. I will tell you that this is going to be a bonus question on your test. So you'll get some practice on your quest assignment. There are 2 problems that involve the Doppler effect, but as far as actually remembering how to solve these on your test, it is going to be a bonus. So go ahead and write these formulas down, and then I defined what each of the variables are for you over to the side. And then when we look at our source moving away from an observer, everything is going to be switched. Now our wavelength has increased, so it's a bigger or larger wavelength. Remember, frequency is the opposite, so that's going to be smaller. And a small frequency means a lower pitch. Now the formula looks really similar, except the only thing that changes is the minus sign from before now becomes a plus sign. Again, this is going to be a bonus question on your test, but it might be a good idea to go ahead and write it down so that you can work the quest problem in those questions. And then I identified all the variables for you to the side. So to summarize on Doppler, we have just a few notes for you. The speed of sound itself is independent of the source's motion. The speed of sound is actually only going to depend on the temperature of the air. So it's going to remain the same. It's constant the whole time. The wavelength and the frequency, however, are changing. And what you hear will be a different frequency depending on if the sound is coming towards you or away from you. And then also, this is really important, the actual frequency that comes out and is emitted by the source is not changing. You only hear it differently because it's moving. And we are going to have a moving sound in class, and we'll make it come towards you and away from you so you can hear those differences in the pitches. So again, we're going to have a demonstration in class so you can actually hear the things that we've learned about in your notes. That's it for this section. In your notes where it says Roman numeral 5 music demo day, those are going to be things that we do all in class together, and I'm going to show you different musical instruments, and we'll talk about wavelength and frequency and resonance and how that applies to our different instruments. So bring those notes with you so you can write down information in class as we review for your test. Thank you.